Robyn Munoz. I'm a PhD student in the University of Portsmouth in the UK, and I work in the Institute of Cosmology and Gravitation with my supervisor, M.Bruni. Our work that I will present to you today is about simulations of a quasi-spherical collapse from initial curvature perturbation. So, why are we interested in this? Well, there are lots of relativistic effects, such as gravitational lensing, gravitational waves, and so on. And we're interested in understanding their impact in cosmology on the growth of large-scale structures specifically. So for this, we use numerical relativity simulations using the Einstein Toolkit code to understand the growth of large-scale structures. We consider simulations of a inhomogeneous Lambda CDM universe in the matter-dominated era. We use the dust-perfect fluid approximation and the synchronous comoving gauge. Inhomogeneities are introduced as fully growing modes defined from the curvature perturbation RC. For this, we use the derivation of this article. The initial distribution in the simulation is that of a three-dimensional sinusoidal. This is slightly more realistic and a good point of comparison with the spherically symmetric top-hat model. So we will study the growth and virialisation / collapse of this structure. And we can also compare to this previous article where they had the same type of distribution but had a growing and decaying mode present in their simulation, so we will be able to measure the impact of that. But before going any further, let me introduce the structure of this video. Here you have on the left-hand side the timestamps of the different sections, and I will start with an introduction to numerical relativity. Then I will discuss the initial conditions and the initial distribution with the implications of that. Then I will present the linear evolution of this system. Then, to understand what we compare, I will briefly introduce the top-hat model in this article. The comparison and the study of the collapse will then be in this section, upon which I will conclude. So first, let's have an introduction to numerical relativity. So for this, we use the n+1 or ADM formalism. This splits the line element into spatial and temporal parts, such that at each timestamp of the simulation, there is a hypersurface or slice that is described by the spatial metric gamma ij. Then we also have the normal to the slice n, and together they provide the extrinsic curvature, and this will indicate the expansion, contraction of the coordinates. Then to go from one timestamp to the next, we apply the lapse along the normal to the hypersurface, and then the shift on the next hypersurface. Then to fully describe the movement of the coordinates, you also need to take into account the time-independent part. And so each grid position in the simulation will have all of these parameters associated to it. What I presented is the more general case, when actually I use the synchronous comoving gauge. This means that the lapse is 1 and the shift is 0. So this simplifies the line element as such. And what this does is that it tilts the hypersurface in such a way that the normal to the hypersurface actually corresponds to the fluid velocity. And so the expansion, contraction of the coordinates is related to the expansion, contraction of the fluid. So the extrinsic curvature is related to the expansion tensor, and this gives a nice meaning to these coordinates. I have introduced a good number of parameters so far, but actually the system of equations that they provide is not strongly hyperbolic. So should you run a simulation with these, your simulation would quickly crash. So a conformal transformation to the BSSN formalism is needed to have a system of equations that is strongly hyperbolic. Then for the matter, something similar is done where we go from the primitive variables to the conserved variables, and these are the quantities that are actually evolved in the simulation. However, these all then get translated back, and these are the quantities that we work with in our data analyses. To monitor the simulation and know if it's working, we can monitor the momentum constraint and the Hamiltonian constraint that are both obtained from the Einstein's equations. Should you apply the FLRW metric to these, you will see that the momentum constraint cancels out and the Hamiltonian constraint becomes the first Friedmann equation. The second Friedmann equation is obtained from the Ricciarduri equation that is retrieved from the Ricci identity. And then the continuity equation is obtained from the conserved equation. And so, should you consider a perturbed FLRW metric, these are the more general equations that you should consider. Now, for the initial conditions, we use the derivation of this article here, and so we start with a flat FLRW metric, where here we have proper time and Cartesian coordinates, and here A is the scale factor. And so we fully perturb this metric here, and we do the same for the matter, where we perturb the energy density, Rho. And so here you have delta that corresponds to the density contrast that you may be familiar with. And so we use the synchronous comoving gauge. This means that we cancel out temporal perturbations, and this also means that the energy density and the determinant of the spatial metric are directly proportional to one another. And then we also cancel out vector and tensor perturbations, because from inflationary models, vector and tensor perturbations are expected to be subdominant during the matter-dominated era. So here we only consider scalar perturbations. Okay, so the spatial metric is then perturbed with psi and a traceless tensor constructed from the scalar chi. So this metric provides the free Ricci scalar here expressed, and here we have it expressed at first order. The part in the brackets corresponds to the curvature perturbation, and this is interesting because the curvature perturbation is one of the variables with zeta that is used to quantify perturbations created during inflation. And it is also gauge invariant at first order, and it is also time independent. So what is done in this article is they expressed these free scalar perturbations as a function of RC. So we only need to define RC to completely express the whole system. And so to do this, what they did is, first they considered the evolution of the density contrast. And so you have this differential equation here, where you see that delta has two solutions, the homogeneous solution and the particular solution. The homogeneous solution corresponds to the decaying mode that is related to the Hubble expansion, and then the particular solution is related to the curvature perturbation. And so in the matter-dominated era, the decaying mode is expected to have fully decayed away, so we only consider the particular solution in this case. And so we can then express delta as a function of RC. then for psi and chi, the continuity equation and the Hamiltonian constraint are used to express them as a function of RC. And so now we have the spatial metric expressed up to first order as a function of RC. We can use that to derive the extrinsic curvature and then also have that defined up to first order. The other parameters here are obtained from the Lambda CDM model, and we define those using the Planck data. We could do the same with the matter density. However, we do one better and use the Hamiltonian constraint, where the various quantities here are computed in full from the first order expressions. So then we have the matter density in full. And so all that is left to do is to define RC. RC is defined as a three-dimensional sinusoidal, where we keep the amplitude and the wavelength of the perturbation as free parameters. The initial redshift also remains free, however we make sure to remain in the matter-dominated era. Let's see what this looks like. So we have one period in the box and we use periodic boundary conditions. This means that we have one overdensity and one underdensity. And you can see these videos, they show isocurves of the density contrast. And so you see that when we are close to the peak of the overdensity or the trout of the underdensity, we are close to spherical symmetry. But as we go further out, we see these filamentary structures. And so those are the reason why we call this a quasi-spherical distribution. Should you look at the x and y is equal to z plane, here you have delta again. You can see the overdensity and the underdensity here with the various filamentary type structures. But you can also look at other parameters that show a reflection of this structure, such as the contrast in the determinant of the spatial metric. This will give us a notion of the volume element compared to the background. And then we also have the contrast in the trace of the extrinsic curvature. And so this will give us a notion of the expansion compared to the background. And then finally here you have the 3 Ricci scalar, and this obviously gives you a notion of the shape of space in those various locations. Now we look at the impact of the 3 parameters. So we have the amplitude and wavelength of the perturbation, as well as the initial redshift of the simulation. And so we look at their impact on the contrasts and the 3 Ricci, and we look at their initial values at the peak of the overdensity. So we see that as we increase a pert, we increase the amplitude of the perturbation. Then the same happens when we look at smaller and smaller redshifts, and when we look at larger and larger wavelengths, the amplitude of the perturbation decreases. So let's look at interesting features. So you see that there are thin lines here. The thin lines correspond to the first order solutions that I listed below. And the thick lines correspond to the full solution obtained from the equations I presented to you previously. And so when you see a separation between the thick and the thin lines, it indicates a nonlinear domain. And so you see this happening on small scales, at low redshift, and for large perturbations. Another interesting feature is this plateau here that you see at large wavelengths and at large redshift, and then this peak here is indicative of a sign change. So this is delta gamma, the contrast in the volume element, and you can see if you look at the first order expression, this is obtained from 2 terms, delta and RC. And so delta gamma will have a matter-dominated part, that is the part that is linear here, and a curvature-dominated part, that is the plateau. And that is obtained when this equation is satisfied. And so this is always for perturbations of wavelengths that are superhorizon. And so when you think of a overdensity, it is a compact region of space. And so intuitively, you would say that the volume element is smaller than the background. And this is what you observe here in the matter-dominated part. But actually in the curvature-dominated regime, you have a sign change, and so the opposite happens. The volume element is larger in the overdensity compared to the background. So that's an interesting feature from there. Now, let's evolve the system. So for that, I used the Einstein Toolkit code. The way this code works is that it divides its various tasks by using different modules. These modules are called thorns. And so for me to provide my initial conditions and my initial distribution to this code, I needed to write my own thorn for this. And so this is called ICPert FLRW. It is written in Fortran, and it provides the initial setup to the thorn called CT dust that is written by E.Bentivegna. So let's see what we get from this. This is for a linear simulation, and you see here I plotted the various contrasts and the conformal free Ricci, and I plotted these throughout the simulation at specific locations. Now let's first look at the overdensity. So the overdensity will have a higher density than the background, and this will grow throughout the simulation. The volume element will be smaller and continue to decrease in size throughout the simulation compared to the background. And the expansion of that region will be slower and slower compared to the background. Then you can see that the curvature is that of a closed universe in this location, and this remains constant in the simulation. Okay, and so in the trout of the underdensity of the bottom of the void, you can see that the density decreases here, the volume element increases, and the expansion is accelerated compared to the background, and you get an open universe in this location. Okay, so let's get this simulation collapsing. So before that, a bit of theory. So the top hat model describes a perfectly spherically symmetric overdensity in a background universe. And so if you were to take a one-dimensional cut of this distribution, you will see that it creates a top hat, hence the name. So on the right-hand side, you see the radius versus time, and so the radius of this overdensity. And so initially, the radius will expand with the expansion of the universe, but eventually it will reach a maximum radius. It will reach the turnaround point. After that, the radius will decrease, and so the structure will collapse or virialize. If you were to imagine various shells composing this overdensity, the outermost shell will reach the turnaround point first, and then it will be the second outer shell, and so on and so forth. And as they contract inwards, they will then cross each other. And so all of these various events happen at specific instances with specific density contrasts, and so we will see if we can reproduce those. E.Bentivegna and my supervisor M.Bruni, they previously ran simulations of a similar setup with a different initial approach. So they defined the density contrast as a three-dimensional sinusoidal, and then set the extrinsic curvature as constant, corresponding to that of the background. Then to get gamma, they used an elliptic solver that Eloisa wrote. It's called CT multilevel, that works with Einstein Toolkit. So introducing perturbations in this manner works, however it introduces a growing and decaying mode, whereas in our case we solely have a growing mode, so we can directly consider the impact that gives. And so they had multiple simulations, and we will focus on the one that is collapsing. And so we start with the same initial setup, amplitude, wavelength, and so on. And we see that the overdensity quickly departs from linearity. So there's a separation between the full line here and the dotted line. And so as the overdensity collapses, the density contrast goes to infinity. And this is what we observe in the simulation, but this is also a hydrodynamics simulation, and so that cannot portray virialisation. Then for the volume element, as it contracts, the volume goes to 0, so the contrast goes to -1, and you see that departures from linearity aren't necessary for the system to remain physically realistic. And so you see at the beginning here, I zoomed in and you can see there's a sign change. This sign change is what I was talking about previously. It is what happens when you start with a perturbation that is in the curvature dominated regime. And then for the extrinsic curvature, you see that initially it expands with the universe, but not as fast. It slows down, and then it reaches a point where the extrinsic curvature is 0. So the contrast is -1. And so at that point it stops, and then it turns around and it collapses inwards. And then for the conformal free Ricci, we see that it starts out initially with a closed curvature, and then it continues to be even more closed, and at the collapse it kind of rips. Then in the void, the density contrast goes to 0, the volume element significantly expands, the expansion is faster than in the background, and we could say that it tends towards the Milne model. That is a model where there is no energy density. But the simulation collapses before that, so we can't say really. And then we see that the curvature is that initially of an open curvature, but then it tends towards flatness. Okay, so let's compare what is happening at the different instances of the turnaround and the virialisation. So we see here that we reach the turnaround point significantly earlier than in the case of Eloisa and Marco's simulation, and we also reached the crash much sooner. And so we can say that because the main difference here is the presence of the decaying mode, we can say that the decaying mode is what slows down their simulation, and we can measure the impact of that here. And then if we compare our results to that predicted by the top hat model, we see that actually we reach the turnaround very almost instantaneously compared to the top hat. And this is also the case when we look at the amplitude of the density contrast at the turnaround. We can't say about the collapse, since this is the virialized expectation, and we have a crash there. So we can say that at the peak of the overdensity, the spherically symmetric top hat model is a very good approximation. Now let's look at what is happening around the peak of the overdensity. And now remember, we're working with a quasi-spherical distribution, and so the direction you're looking in from the peak of the overdensity matters. And so that's why we are considering 3 different sets of directions. And so A, the first one, is along the main axis, x, y, z, around the peak of the overdensity. And so these are the directions where you would have the filamentary structure that I described before. And so if you take a radial profile of the density contrast, you see that in this direction you have a smaller spread of the density contrast compared to the other ones. The other ones, starting with B, this direction corresponds to the direction midway through the main axis, and here you have a larger range of delta values, and this section goes through an underdense part. And then the last one, direction C, goes through the middle of the faces, and this is a direction that will have the underdensity as well. And so you can see that close to the peak of the overdensity you do have strong spherical symmetry because the directions don't seem to matter that much, but as you go further out you do see that it does make a difference. To measure the instance where a region in space goes through turnaround when it goes from expansion to infall, you consider the trace of the extrinsic curvature, and when that is 0, it's when it changes sign. And so the peak of the overdensity is the region in space that goes through this transition first, and when you look at the simulation at a later point in time, here you have a plane of x, y, and you have the trace of the extrinsic curvature. So you look at a later point in time and you see this ring, this transitional ring, where on the outside you have expansion and on the inside you have infall. And so the infalling region is expanding around the peak of the overdensity. And so initially this seems quite spherical, but when you look at it at a later time, you see that it is not spherical. It has a distinct shape where the direction you're looking in does matter. So let's consider this this radius that we're calling the turnaround radius, depending on the direction we're looking at. This is what is plotted here. You have the turnaround radius and the 3 directions. So initially, no matter the direction, it progresses in a similar fashion. Then where you have the highest density contrast are the directions where the turnaround radius expands the most. And so this is the background proper distance, but because each grid position in the simulation box has an associated metric, you can use that to calculate the proper distance. And this is what is presented in the second plot. So here you have again a turnaround radius, but in proper distance. And you see that you have the same behavior, but the overall expansion is not as great because the metric is perturbed as well. And you can see that actually in the directions where the direction goes through an underdense region of space, you can see that the radius stops expanding and decreases. So the infall region has nothing more to accumulate in this direction, and so stops expanding and then goes down. So that's an interesting feature. Another way to look at what is happening around the peak of the overdensity is to consider the contributions to the Relativistic equation. So they are plotted here along the diagonal going directly through the simulation box, such that here, if you look at the red term, you have the overdensity on one side and the underdensity here. Okay, and we look at this at 2 instances. So if you look at the expansion, you see that this instance corresponds to the moment where the peak of the overdensity has the smallest expansion, so it is at the turnaround point there. And then we look at the part that is right before the crash, and we see that the expansion outlines a region that is much bigger and is the infalling region. An interesting term here amongst these is the shear in green. We see that it is very small but non-zero, and we see that it is smallest at the peak of the overdensity and trout of the underdensity, so where there is the most spherical symmetry. And this is also visible right up to the part right before the crash. So that's interesting. Let's look at the general equations that I presented in the introduction to numerical relativity. So if you cancel out the shear from these two equations, you see that you become independent of your environment in this specific location. And so then you retrieve the Friedmann equations. And so the peak being independent of its environment is the reason why it matches the top hat model so well. So let's recap. I have presented the initial setup of the thorn I developed called IC-PERT FLRW. And for this initial setup, I have identified the long wavelength regime, or the curvature-dominated regime, as well as the linear versus non-linear regimes, so that we have the freedom to start simulations with perturbations within the validity of the first-order perturbation theory. Using this, I compared my simulations to those provided in this article and I found that the decaying mode present in their simulations slowed down the virialisation or crash that they had. And so then at the peak of the overdensity, I found that it is a very good approximation to the top hat model, and this is because the peak is independent of its environment. And then we also described the expansion of the turnaround radius, and depending on the direction and structure that we're working in. Following from this, there are lots of future ventures that are to be considered, but for now, thank you for your attention, and I would like to thank the organizers for giving me the opportunity to present my work. Should there be any questions, I will remain available throughout this conference. Otherwise, you can reach me at the following email address. Thank you.